What are the best solutions and technologies to recycle pollution, waste, and greenhouse gases into industrial-grade feedstocks and materials? There are several technologies and solutions aimed at converting pollution, waste, and greenhouse gases into industrial-grade feedstocks and materials. Some of these innovative approaches include waste-to-energy, WTE. Technologies such as incineration and gasification can convert solid waste into energy. The generated heat can be used for electricity generation or industrial heat. Waste-to-energy is a broad term that encompasses various technologies designed to convert solid waste into energy. This approach not only helps in waste management, but also contributes to the generation of electricity and industrial heat. Two common WTE technologies are incineration and gasification. Incineration process. Incineration involves the controlled burning of solid waste at high temperatures. The heat generated during combustion is harnessed to produce steam, which then drives turbines to generate electricity. Energy recovery. The primary purpose of incineration is energy recovery, and it reduces the volume of waste by up to 90%. The heat produced can also be used for district heating, providing warmth to nearby buildings. Emission control. Advanced incineration facilities are equipped with pollution control technologies to minimize emissions. These systems capture and treat pollutants, ensuring compliance with environmental regulations. Gasification process. Gasification is a thermochemical process that converts solid waste into syngas, a mixture of hydrogen and carbon monoxide, in the absence of direct combustion. The syngas can then be used for electricity generation or as a feedstock for the production of chemicals and fuels. Flexibility. Gasification offers greater flexibility in handling various types of waste, including biomass and organic materials. It allows for the efficient conversion of a wide range of feedstocks into energy or valuable products. Reduced emissions. Gasification typically produces lower emissions compared to traditional incineration, and the process can be designed to capture and utilize byproducts effectively. Key advantages of WTE technologies. Waste reduction. WTE technologies significantly reduce the volume of solid waste, helping to address the challenges associated with landfills and overflow and waste disposal sites. Energy generation. The primary benefit of WTE is the generation of electricity or industrial heat from waste materials, contributing to a more sustainable energy mix. Resource recovery. WTE processes can extract valuable materials or energy from waste streams, promoting resource recovery and minimizing the environmental impact of waste disposal. Land use optimization. By converting waste into energy, WTE helps optimize land use by reducing the reliance on landfill space. Challenges and considerations. Emission control. Ensuring effective emission control systems is crucial to minimize the environmental impact of combustion processes. Feedstock quality. The composition and quality of waste feedstock can affect the efficiency of WTE technologies. Contaminants and hazardous materials in the waste stream need to be carefully managed. Public perception. WTE facilities sometimes face opposition from communities due to concerns about emissions, odors, and potential health impacts. Public awareness and engagement are essential in addressing these concerns. Technological advances. Continuous research and development are needed to improve WTE technologies, enhance energy efficiency, and reduce environmental impacts. Carbon capture and utilization, CCU. This involves capturing carbon dioxide (CO2) emissions from industrial processes and using them as a feedstock for various products. Examples include using CO2 to produce chemicals, fuels, or construction materials. Carbon capture and utilization, CCU, is a process that involves capturing carbon dioxide (CO2) emissions from industrial activities and using them as a valuable resource to produce various products, CCU contributes to mitigating climate change by reducing greenhouse gas emissions while creating economic opportunities through the utilization of captured carbon. Here are key aspects of carbon capture and utilization. Capture technology, post-combustion capture. In this method, CO2 is captured after the combustion of fossil fuels in industrial processes such as power plants. The captured CO2 is then separated and purified for utilization. Pre-combustion capture. CO2 is captured before the combustion of fossil fuels, typically in gasification processes. This allows for the separation of CO2 before it is released into the atmosphere. Utilization pathways. Chemical production. CO2 can be used as a feedstock for the production of chemicals, such as methanol, which is an essential industrial building block. Fuel synthesis. CO2 can be converted into synthetic fuels, including synthetic natural gas or even liquid hydrocarbons, through processes like Fischer-Tropsch synthesis. Construction materials. CO2 can be mineralized and used in the production of construction materials such as concrete, enhancing sustainability in the building industry. Plastics and polymers. CO2 can be incorporated into the production of plastics and polymers, contributing to the development of more environmentally friendly materials. Benefits of CCU. Emission reduction. CCU helps reduce CO2 emissions from industrial processes, contributing to climate change mitigation. Resource utilization. Instead of being treated as a waste product, captured CO2 becomes a valuable resource for the production of various materials, promoting circular economy principles. Economic opportunities. CCU creates new economic opportunities by developing industries that utilize captured CO2, fostering innovation and job creation. Carbon neutrality. In some cases, the utilization of CO2 can lead to products with a carbon neutral or even carbon negative footprint, depending on the overall life cycle. Challenges and considerations. Energy requirements. Some CCU processes may require significant energy inputs, and the overall sustainability of the approach depends on the energy source used. Economic viability. The economic viability of CCU projects depends on factors such as carbon pricing, market demand for the produced materials, and the cost of capture technologies. Scale and deployment. Widespread deployment of CCU technologies requires scaling up operations and overcoming technical, regulatory, and infrastructure challenges. Biomass conversion. Organic waste, agricultural residues, and other biomass materials can be converted into biofuels, bio-based chemicals, and biodegradable plastics through processes like fermentation and pyrolysis. Biomass conversion is a process that transforms organic materials, such as agricultural residues, organic waste, and other biomass feedstocks, into valuable products like biofuels, bio-based chemicals, and biodegradable plastics. This approach is part of the broader effort to utilize renewable resources and reduce dependence on fossil fuels. Two common methods of biomass conversion are fermentation and pyrolysis. Fermentation process. Fermentation involves the biological conversion of biomass, typically sugars or starches, into biofuels or bio-based chemicals through the action of microorganisms such as bacteria, yeast, or fungi. Biofuels, ethanol, for example, can be produced through the fermentation of sugars derived from biomass. This bioethanol can be used as a renewable fuel in transportation. Bio-based chemicals. Microorganisms can also be engineered to produce bio-based chemicals, including organic acids, solvents, and other valuable compounds. Pyrolysis process. Pyrolysis is a thermal decomposition process that breaks down biomass in the absence of oxygen, producing bio-oil, biochar, and syngas. Pyrolysis can handle a wide range of biomass materials, including wood, agricultural residues, and municipal solid waste. Biofuels. The bio-oil obtained from pyrolysis can be refined into biofuels such as biogasoline, biodiesel, or aviation fuels. Biochar. Biochar, a carbon-rich material, can be used as a soil conditioner, improving soil fertility and sequestering carbon. Syngas. Syngas produced during pyrolysis can be used as a precursor for the production of bio-based chemicals and fuels. Benefits of biomass conversion. Renewable energy. Biomass conversion provides a renewable source of energy, reducing reliance on fossil fuels and contributing to a more sustainable energy mix. Waste valorization. Biomass conversion allows for the utilization of organic waste materials, diverting them from landfills and turning them into valuable products. Reduced greenhouse gas emissions. Biofuels produced from biomass conversion generally have lower greenhouse gas emissions compared to traditional fossil fuels, contributing to climate change mitigation. Biodegradable plastics. Biomass conversion can be used to produce biodegradable plastics from renewable sources, offering an eco-friendly alternative to traditional plastics. Circular economy. By converting biomass into bio-based products, biomass conversion supports circular economy principles by closing the loop on waste streams and promoting resource efficiency. Challenges and considerations. Feedstock availability. The availability and sustainability of biomass feedstocks can be a limiting factor for large-scale biomass conversion projects. Economic viability. The economic viability of biomass conversion processes depends on factors such as feedstock costs, technology efficiency, and market demand for the end products. Competition for land use. There is a need to carefully manage land use to prevent competition between biomass crops for energy production and food crops for consumption. Plasma gasification. This technology uses high-temperature plasma to break down waste materials into syngas, a mixture of hydrogen and carbon monoxide, which can then be used to produce fuels and chemicals. Plasma gasification is an advanced waste-to-energy technology that utilizes high-temperature plasma to break down waste materials into syngas, a mixture of hydrogen and carbon monoxide. This process takes place in a controlled environment with temperatures reaching thousands of degrees Celsius. Plasma gasification offers several benefits and has applications in waste management and the production of fuels and chemicals. Here are the key aspects of plasma gasification. Process overview. Plasma generation. High-temperature plasma is created by applying an electric field to a gas, typically a mixture of air and steam, causing it to ionize and form a plasma state. Waste conversion. Waste materials, including municipal solid waste, industrial waste, and hazardous waste, are fed into the plasma chamber. The intense heat of the plasma breaks down the complex organic and inorganic components of the waste into simpler molecular structures. Syngas formation. The resulting syngas is composed of hydrogen, carbon monoxide, and other gases. Syngas can be further processed to extract valuable components or used as a fuel source. Applications. Energy generation. The syngas produced in plasma gasification can be used as a clean and efficient fuel for electricity generation or for industrial heat applications. Chemical production. Syngas is a versatile feedstock for the production of chemicals, including methanol, ammonia, and other valuable compounds. Waste management. Plasma gasification reduces the volume of waste and can be an environmentally friendly alternative to traditional incineration methods. Advantages of plasma gasification. High temperatures. The extremely high temperatures achieved in plasma gasification allow for the breakdown of complex waste materials, including hazardous substances. Syngas composition. The syngas produced is rich in hydrogen and carbon monoxide, which are valuable for various industrial applications. Reduced emissions. Compared to traditional incineration, Plasma gasification tends to produce lower emissions and has the potential for cleaner and more efficient waste-to-energy conversion. Challenges and considerations: cost and scalability. The initial capital costs of plasma gasification facilities can be high, and the technology's scalability for widespread adoption needs to be addressed. Feedstock composition. The efficiency of plasma gasification may be influenced by the composition and variability of waste materials, requiring careful feedstock management. Technology development. Ongoing research and development are necessary to optimize the technology, improve efficiency, and address operational challenges. Environmental impact. Plasma gasification has the potential to contribute to environmentally sustainable waste management by reducing the volume of waste sent to landfills and minimizing emissions associated with traditional disposal methods. Circular economy initiatives. Implementing circular economy principles involves designing products for recyclability, encouraging recycling, and reusing materials. This reduces the generation of waste and promotes the sustainable use of resources. Circular economy initiatives are designed to shift away from the traditional linear take, make, dispose model and move towards a more sustainable and regenerative system. These initiatives prioritize the efficient use of resources, waste reduction, and the promotion of recycling and reusability. Here are key aspects of circular economy initiatives. Design for recyclability. Circular economy principles begin at the product design stage. Designing products with recyclability in mind involves selecting materials that are easy to recycle, minimizing the use of complex or mixed materials, and ensuring that products can be disassembled at the end of their life cycle. Emphasizing design for recyclability helps create a closed-loop system where materials can be recovered and reused in the manufacturing of new products. Recycling infrastructure. Investing in recycling infrastructure is crucial for the success of circular economy initiatives. This includes establishing efficient and accessible recycling facilities for various types of materials, such as plastics, metals, paper, and glass. Improving waste collection systems and implementing sorting technologies contribute to more effective recycling processes. Extended producer responsibility, EPR. EPR is a regulatory approach that holds producers responsible for the entire life cycle of their products, including collection, recycling, and disposal. This encourages manufacturers to design products with longevity and recyclability in mind. EPR programs can create economic incentives for companies to adopt circular economy practices. Reuse and repair programs. Encouraging the reuse and repair of products promotes a culture of extending the life of goods. Initiatives such as community repair workshops, second-hand markets, and product refurbishment programs contribute to reducing waste and resource consumption. Businesses can implement take-back programs, where they take back used products from consumers for refurbishment or recycling. Digital technologies and tracking. Digital technologies, such as blockchain and Internet of Things, IoT, devices, can be employed to track and trace materials throughout their life cycle. This transparency helps in ensuring that materials are recycled, reused, or disposed of responsibly. Digital platforms can facilitate the sharing or renting of products, promoting collaborative consumption and reducing the demand for new goods. Product as a service models. Shifting towards service-oriented models, where consumers pay for the use of a product rather than owning it, can incentivize manufacturers to design durable and easily maintainable products. This approach can extend the life of products and reduce the overall demand for raw materials. Education and awareness. Raising awareness among consumers, businesses, and policymakers is crucial for the success of circular economy initiatives. Educating the public about the benefits of recycling, reusing, and reducing waste fosters a mindset of sustainability. Businesses can play a role by communicating the environmental benefits of their circular practices and promoting responsible consumption. Policy and regulation. Governments can play a significant role in advancing circular economy initiatives by implementing supportive policies and regulations. This may include incentives for circular business models, regulations promoting recyclability, and restrictions on certain single-use items. Algae-based solutions. Algae can capture CO2 from industrial emissions and wastewater. Additionally, algae can be processed to produce biofuels, bio-based materials, and nutritional supplements. Algae-based solutions leverage the unique properties of algae to address environmental challenges and provide sustainable alternatives in various industries. Algae, a diverse group of photosynthetic organisms, can play a significant role in capturing carbon dioxide (CO2) from industrial emissions and wastewater. Additionally, algae can be processed to produce biofuels, bio-based materials, and nutritional supplements. Here are key aspects of algae-based solutions. CO2 capture. Algae have the ability to absorb and utilize carbon dioxide during photosynthesis. This makes them effective in capturing CO2 emissions from industrial processes and power plants. Integrating algae into industrial facilities or wastewater treatment plants provides a natural and biological method for carbon sequestration. Biofuel production. Algae are rich in lipids, which can be converted into biofuels such as biodiesel. Algal biofuels offer a sustainable alternative to traditional fossil fuels and can be produced on non-arable land, reducing competition with food crops. The cultivation of algae for biofuel production has the potential to contribute to renewable energy goals and mitigate greenhouse gas emissions. Bio-based materials. Algae can be processed to extract various compounds, including polysaccharides and proteins, which can be used in the production of bio-based materials. Algal-derived materials can find applications in bioplastics, packaging, and other industries, providing eco-friendly alternatives to conventional materials. Nutritional supplements. Certain types of algae, such as spirulina and chlorella, are rich in nutrients and have been used as dietary supplements. Algae-based nutritional supplements are known for their high protein content, essential amino acids, vitamins, and minerals. They are considered a sustainable source of nutrition. Wastewater treatment. Algae can be employed in wastewater treatment processes to remove nutrients such as nitrogen and phosphorus. This helps in reducing water pollution and improving the quality of discharged water. Algae-based wastewater treatment systems provide an environmentally friendly and cost-effective solution for nutrient removal. Carbon utilization and circular economy. Algae-based solutions contribute to a circular economy by utilizing CO2 emissions as a resource for algal growth. By integrating algae into industrial processes, CO2 emissions are transformed into valuable products, aligning with circular economy principles. Biomass production for multiple uses. Algae can be cultivated for biomass production, providing a versatile feedstock for various applications. Depending on the species and cultivation methods, algae can be utilized for bioenergy, animal feed, bioremediation, and other purposes. Research and innovation. Ongoing research is exploring new strains of algae, optimizing cultivation techniques, and improving processing methods to enhance the efficiency and economic viability of algae-based solutions. Innovations in algae biotechnology continue to expand the range of applications and increase the overall sustainability of these solutions. Biogas production. Organic waste can be anaerobically digested to produce biogas, which is primarily composed of methane. Biogas can be used for energy production or as a feedstock for the production of chemicals. Biogas production is a sustainable process that involves the anaerobic digestion of organic waste to generate biogas. This renewable energy source is primarily composed of methane, CH4, and carbon dioxide CO2, with smaller amounts of other gases. Biogas can be utilized for energy production, and its byproducts can serve as valuable resources. Here are key aspects of biogas production. Anaerobic digestion process. Anaerobic digestion is a biological process in which microorganisms break down organic materials in the absence of oxygen. This process occurs in a controlled environment, such as a biogas digester or anaerobic reactor. Organic waste feedstock. Various organic materials can be used as feedstock for anaerobic digestion, including agricultural residues, food waste, sewage sludge, and manure. Biogas formation. During anaerobic digestion, microorganisms decompose organic matter, producing biogas as a result of the metabolic processes. Biogas typically consists of methane, CH4, and carbon dioxide, CO2. Biogas composition. Methane, CH4. Methane is the primary component of biogas, usually ranging from 50% to 70% or higher. Methane is a potent greenhouse gas, and capturing it for energy use helps mitigate its environmental impact. Carbon dioxide, CO2. Carbon dioxide is the second major component of biogas, comprising a significant portion of the gas mixture. Trace gases. Small amounts of other gases, such as hydrogen sulfide, H2S, nitrogen N2, and water vapor, may also be present. Energy production. Electricity generation. Biogas can be burned in a combined heat and power (CHP) system to generate electricity and heat simultaneously. This electricity can be used on-site or fed into the grid. Heat production. The heat generated during biogas combustion can be utilized for various purposes, including space heating, industrial processes, or even in greenhouses. Renewable natural gas (RNG). Upgrading biogas. Biogas can be upgraded to produce renewable natural gas (RNG), which is almost pure methane. RNG can be injected into the natural gas grid or used as a clean transportation fuel. Vehicle fuel. RNG is gaining popularity as a sustainable alternative for fueling vehicles, contributing to reduced greenhouse gas emissions in the transportation sector. Waste management. Reducing methane emissions. By capturing methane through biogas production, organic waste is effectively treated, and methane emissions, otherwise released into the atmosphere during decomposition, are mitigated. Waste energy. Biogas production supports a waste-to-energy approach, providing a sustainable solution for the management of organic waste. Agricultural benefits. Nutrient-rich digestate. The byproduct of anaerobic digestion, known as digestate, is a nutrient-rich material that can be used as an organic fertilizer in agriculture, closing the nutrient loop. Potential for chemical production. Feedstock for chemicals. Biogas can serve as a feedstock for the production of chemicals and materials through further processing and refinement. Carbon mineralization. Certain technologies aim to capture CO2 emissions and convert them into stable mineral forms. This process, known as carbon mineralization or mineral carbonation, can provide a long-term storage solution for carbon. Carbon mineralization, also known as mineral carbonation, is an innovative process that involves capturing carbon dioxide (CO2) emissions and converting them into stable mineral forms. This method provides a potential long-term storage solution for carbon by transforming gaseous CO2 into solid carbon or minerals. Here are the key aspects of carbon mineralization. Process overview. Reaction with minerals. Carbon mineralization involves the reaction of CO2 with certain types of minerals, typically metal oxides or silicate minerals. This chemical reaction results in the formation of stable carbon minerals. Formation of carbonates. During the reaction, the CO2 combines with metal cations released from the minerals to form solid carbonates, such as calcium carbonate, CaCO3, or magnesium carbonate, MCO3. Natural and accelerated processes. Natural carbonation. In nature, Carbonation occurs over geological timescales as CO2 reacts with minerals in rocks. This natural process contributes to the long-term storage of carbon in the Earth's crust. Accelerated carbonation. Carbon mineralization technologies aim to accelerate this natural process by optimizing conditions and using specific mineral feedstocks. This allows for the capture and storage of CO2 on a much faster timescale than natural geological processes. Sources of minerals. Mining residues. Certain mining residues, such as serpentine and olivine, are rich in minerals that can undergo carbonation reactions with CO2. Using these mining byproducts as feedstock supports both carbon capture and waste utilization. Industrial wastes. Some industrial byproducts, such as steel slag, may also be suitable for carbon mineralization, providing an opportunity for recycling waste materials. Long-term carbon storage. Stable carbonates. The carbonates formed through mineral carbonation are stable and resistant to the release of CO2. This offers the potential for long-term carbon storage, reducing the risk of carbon leakage back into the atmosphere. Geological storage. Carbonated minerals can be deposited in geological formations, such as underground mines or depleted oil and gas reservoirs, for secure and long-lasting storage. Carbon utilization and waste reduction. Utilization of CO2 emissions. Carbon mineralization transforms CO2 emissions, which are a major contributor to climate change, into a useful and stable form, contributing to carbon utilization strategies. Waste reduction. By utilizing mining residues or industrial byproducts, carbon mineralization also addresses the issue of waste disposal, turning these materials into valuable carbon sinks. Research and development. Technological advancements. Ongoing research and development efforts are focused on improving the efficiency and scalability of carbon mineralization technologies. This includes exploring suitable mineral feedstocks, optimizing reaction conditions, and assessing the environmental impact. Integration with carbon capture technologies. Coupled with carbon capture, carbon mineralization can be integrated with carbon capture technologies in industrial processes or power plants. This allows for the capture of CO2 emissions at the source before converting them into stable carbonates. Recycling technologies. Advanced recycling technologies for plastics, metals, and other materials help transform waste into high-quality feedstocks for new products, reducing the need for virgin materials. Recycling technologies play a crucial role in the sustainable management of waste by transforming materials into high-quality feedstocks for the production of new products. Advanced recycling technologies are designed to efficiently process various materials, including plastics, metals, and other recyclables. These technologies contribute to the circular economy by minimizing the reliance on virgin materials and reducing environmental impacts. Here are key aspects of recycling technologies: plastic recycling technologies, mechanical recycling. This common method involves collecting, sorting, cleaning, and processing plastic waste into granules that can be used as feedstock for new plastic products. Mechanical recycling is suitable for plastics with similar properties, such as PET, polyethylene terephthalate, bottles. Chemical recycling, or feedstock recycling. Chemical recycling technologies break down plastics into their original chemical components or convert them into feedstocks for the production of new plastics. Processes like pyrolysis and depolymerization fall under this category. Biological recycling. Enzymatic or microbial processes are being explored to break down plastics into simpler compounds using biological agents, offering a more environmentally friendly approach. Metal recycling technologies. Traditional metal recycling. Conventional metal recycling involves collecting and melting down scrap metal to produce new metal products. Commonly recycled metals include aluminum, steel, copper, and others. Electrolysis. Some advanced technologies use electrolysis to recover metals from electronic waste or complex metal-containing materials. This process allows for the extraction of specific metals in a more controlled manner. E-waste recycling technologies, component recovery, technologies for electronic waste, e-waste, focus on recovering valuable components, such as semiconductors, circuit boards, and precious metals like gold and silver. Separation and extraction methods are employed to maximize resource recovery. Urban mining. Urban mining involves the extraction of valuable metals from discarded electronic devices, contributing to the efficient use of resources and reducing the environmental impact of e-waste. Textile recycling technologies. Mechanical recycling. Textile waste can be mechanically processed to create recycled fibers for new textiles or products. This process involves shredding, cleaning, and respinning textile materials. Chemical recycling. Innovative technologies aim to break down textile fibers into their chemical components, allowing for the creation of new fibers or materials. Glass recycling technologies. Cullet production. Glass recycling involves collecting, cleaning, and crushing used glass containers to produce cullet, which is then melted to create new glass products. Color sorting. Advanced technologies use optical sorting systems to separate glass by color, improving the quality of recycled glass and expanding its applications. Optical sorting and AI. Optical sorting. Advanced sorting technologies use optical sensors to identify and separate materials based on their properties, such as color and composition. This enhances the efficiency of recycling processes. Artificial intelligence, AI. AI applications are increasingly being integrated into recycling facilities to improve sorting accuracy, reduce contamination, and optimize recycling operations. Closed-loop systems. Closed-loop recycling. Some industries are adopting closed-loop systems where materials are recycled and reused within the same production cycle. This minimizes the need for new raw materials and reduces environmental impact. Innovations and research. Continuous innovation. Ongoing research and development focuses on improving existing recycling technologies, developing new methods, and addressing challenges such as contamination and material complexity. Hydrothermal liquefaction, HDL. HDL is a technology that converts organic waste, including sewage sludge and algae, into a liquid bio-oil that can be further processed into fuels or chemicals. Hydrothermal liquefaction is an innovative technology that transforms organic waste, such as sewage sludge and algae, into a liquid bio-oil through a high-temperature and high-pressure hydrothermal process. This bio-oil can serve as a valuable feedstock for the production of biofuels or chemicals. Here are the key aspects of hydrothermal liquefaction. Process overview. High temperature and high pressure conditions. HDL involves subjecting organic feedstock to elevated temperatures, typically between 250 degrees Celsius and 550 degrees Celsius, and high pressures, typically between 10 and 25 MPa, in the presence of water. Liquefaction of biomass. The combination of high temperature and pressure facilitates the liquefaction of the organic feedstock, breaking down complex organic molecules into a liquid bio-oil. Feedstock options. Sewage sludge. HTL can be applied to sewage sludge, a byproduct of wastewater treatment plants. This helps in managing and utilizing sewage sludge more sustainably. Algae. Algae are rich in lipids and can be efficiently converted into bio-oil through HDL. This approach is relevant to both wastewater treatment and the production of biofuels from algae cultivation. Bio-oil composition. Hydrocarbons. The bio-oil produced through HDL contains hydrocarbons, including alkanes, alkenes, and aromatic compounds. Oxygenates. Oxygen-containing compounds such as ketones, aldehydes, and carboxylic acids may also be present in the bio-oil. Water content. The bio-oil typically has a significant water content, and additional processing steps may be required to remove water and impurities. Potential applications: biofuels. The liquid bio-oil produced through HTL can be further processed through upgrading methods, such as hydrotreating, to produce biofuels like renewable diesel or aviation fuels. Chemical feedstock. The bio-oil can also serve as a feedstock for the production of bio-based chemicals and other value-added products. Advantages of HTL: waste valorization. HTL provides a means to valorize organic waste, converting it into a valuable bio-oil and reducing the environmental impact of waste disposal. Versatility. HTL is versatile and can handle various organic feedstocks, making it suitable for different waste streams and biomass types. Liquid form. The bio-oil produced is in liquid form, making it easier to handle and transport compared to solid or gaseous bioenergy carriers. Challenges and considerations. Energy input. HTL requires energy input to achieve the necessary high temperatures and pressures. Optimizing the energy balance is crucial for the overall sustainability of the process. Water content. The presence of water in the bio-oil may require additional processing steps for dehydration. Catalyst selection. The use of catalysts in HTL may influence the yield and composition of the bio-oil, and selecting suitable catalysts is an area of ongoing research. Research and development. Technological advancements. Ongoing research focuses on improving the efficiency of HTL processes, exploring new catalysts, and addressing challenges to enhance the commercial viability of this technology. It's important to note that the effectiveness of these solutions may vary based on factors such as local conditions, waste composition, and regulatory frameworks. Integrating these technologies into a comprehensive and sustainable waste management strategy is key to addressing environmental challenges and promoting a circular economy.